We propose a new method to reconstruct intensity images from event cameras with high-quality details and super resolved dimensions. Event cameras enable vision under large illumination changes, low light conditions, rapid movements, and high-speed motion. Unlike traditional cameras, event cameras output each pixel asynchronously up to microsecond resolution as a stream. This stream of asynchronous events cannot be delivered to image-based vision algorithms or neural networks, so we aggregate them as stacks based on time or the number of events. Event cameras have relatively low size resolutions, and previous event-to-intensity image reconstruction methods aim for same-size outputs using statistical methods or learning-based architectures. We aim to simultaneously reconstruct intensity images with super-resolved dimensions using a recurrent residual design. We use a sequence of stacks over time as inputs, which can be 3, 5, or more. The central stack indicates the timestamp of the output intensity image. The central stack and its next stack are temporally related by the flow estimation network. This flow plus the stacks go to an event feature rectifier EFR to make the events have sharper edges. These rectified events plus a previous state go to the super resolution network SRNet to make the next hidden state plus an intermediate intensity image output IN plus M. This process is repeated with the previous stack as a pair and the central stack by itself. All intermediate intensity images are mixed in the last stage to create the final output image, ON. At training, we compare this output with the ground truth using our similarity metrics. SRNet is a combination of 4 residual networks, with ResNet C being its deepest. We designed the connections so that the reconstructed image mainly relies on new incoming events while also considering previous states. Our dataset is from 2 sources: real-world events with same-size images and simulated data. Unlike the frames from a real-world camera, the simulator's ground truth has HDR properties, is immune to motion blur, and has no limitation on GT size. So we use it mainly for training and do not fine-tune on any other dataset. On real-world events, we compare our reconstructed images to state-of-the-arts by downscaling ours. On simulated events, we compare our super-resolved outputs to state-of-the-art event-to-intensity reconstruction combined with state-of-the-art single or multiple image super-resolution methods. These are some qualitative results on same-size reconstruction and super-resolved reconstruction settings. We use real-world sequences and show that we outperform previous methods in average in terms of the structural similarity SSIM, mean squared error MSE, and a learned metric called the perceptual similarity LPIPS. We also compare our results to EV combined with 2 recent single image super resolution SISR and multiple image super resolution MISR methods in the 4x setting. Our method outperforms both combinations of EV plus SISR and EV plus MISR. Our method is capable of reconstructing high-quality images under challenging and extreme dynamic range conditions. We deliver super-resolved images only from events, but can we reach higher quality outputs by incorporating intensity images as well? We present our extensions, the complementary and duo-pass schemes. The complementary scheme uses the same architecture as our original method, but replaces the central stack with a low-resolution intensity frame to fuse events and images. If we replace the central stack with a reconstruction from the original method, we can reach higher quality outputs only from events by duo-passing. These are some sample outputs from original, complementary, and duo-pass extensions, together with the APS frame for reference. Although we aim for image reconstruction, we can also have consistent videos by using a post-processing method. We here compare our different schemes on real-world sequences and compare to EV. Using our duo-pass and complementary scheme, we can reach even higher quality outputs. The histogram equalized GT is also shown to visualize darker details. Thank you. Find our repo using the URL or QR code.